The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI Web Sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
This presentation has two presenters. The first, Lawrence Valentine, has been involved in design and construction of over 100 structures with Type K and Type G shrinkage comp, but he's unable to present today. Jason Barnes with Green Umbrella, who produces a Type G expansive component, is going to also do the presentation. So with that, Jason.
We wanted to give the direction towards the ACI 223, and we're going to talk about ACI 223 even probably a little more than what we've had in the past presentations. But when this document of the Guide for Use of Shrinkage Compensating Concrete was issued in 2010, it really started a revolution in the shrinkage compensating concrete industry that is spreading into all uses of concrete. Now, two new concepts were introduced into this 2010 ACI 223 that has really changed how shrinkage compensating concrete is manufactured. Now, of these two revolutions, one of them is the Type G shrinkage compensating concrete. And the second one is components, or shrinkage compensating components in conjunction with Type G. Now, this revolution started in August of 2002 with the publication in the Concrete International of test results of shrinkage compensating concrete made with a component. Now, the articles were analyzed by the ACI Committee 223, and it was judged to be equal to shrinkage compensating concrete made with Type K cement and should therefore be incorporated into the 223 document. It was during this process that the expansion mechanism of the component was designated as Type G. Now, here's this revolution number 2 that we're talking about the components, breaking it down. A component that, when added to a standard concrete mix, produces a shrinkage compensating concrete has been available and in use for approximately 4 decades. But the product has never been able to establish a wide acceptance, and it's understandable since it was not included nor was in compliance with ACI 223, and therefore it lacked the credibility and the weight of ACI recognition, the acceptance, and obvious documentation. Therefore, the component should not be specified or could not be specified with any ACI cited reference. And as a result, though, of this ACI 223-R-10, Type G components are now recognized and supported by ACI 223 and have the full credibility and the weight of the ACI recognition, the acceptance, and the documentation, as we mentioned earlier. In practice, components have replaced cements as the methods to produce shrinkage compensating concrete. Now, with the previous issues that we had with ACI 223, they focused on the Type K cements to produce shrinkage compensating concrete. Type K concrete produce their expansion via the producing of the etronite crystals in the concrete. Now, Type G concrete produces that expansion with the production of calcium hydroxide platelets in the concrete. Now, both Type G and Type K concrete start to produce their expansion mechanism the moment water is added to the mix. Type G concrete produces its calcium hydroxide platelets at approximately the same rate and at the same time that concrete is curing and hardening. The Type G maximum expansion is reached within 48 hours. During the same time period that the concrete has experienced its greatest strength and its hardest gains. Now, Type K concrete, in comparison, reaches their maximum expansion during the third, the fourth, or the fifth day. And this is after the concrete is hard enough to produce or to be placed into limited service. Now, the Type G advocates are going to say this, that they will tell you that their system is better because it expands lockstep with the hardening of the concrete. And this is what the Type K people will tell you, that their system is better because the final expansion is achieved after the concrete has hardened. And this is one thing that we could be able to pass on. This friendly debate is really could be considered meaningless, moot, even irrelevant, since the difference in the cure rates taken into account when using the member expansion group or graphs in 223, during the concrete mix design formulation. And the finished products that are produced by both Type G and Type K systems are equal to each other in every measure of quality, and both are of a higher quality than we have with Portland cement concrete of an equal strength. So those are some of the things that we see in regards to those components, but here's some more. When we look at this question could be asked, what is a component and how is it used, especially with this system? There are two excellent questions that can be addressed this way. Components are mineral-based. They're dry, cementitious materials that are added to a standard concrete mix. These components are materials that are inert in the base cement and are modified and added to the concrete mix to enhance and exaggerate beneficial characteristics and properties of native components in the base cement. The core purpose that we've talked about even today of shrinkage-compensating components is to create an expansion mechanism in the concrete mix, as long as that expansion induced in the concrete mix is equal to or slightly greater than the anticipated shrinkage of the concrete mix. The concrete will never go into tension and shrinkage cracking will not or cannot develop. Since this is the essence of shrinkage-compensating concrete, maybe we could be able to repeat that. As long as the expansion included in the concrete mix is equal to or slightly greater than the anticipated shrinkage of the concrete mix, the concrete will never go into tension and the shrinkage cracking will not or cannot develop. Now, this is an image of the Type G platelet. Now, this slide is highly magnified, and it's a picture of a calcium hydroxide platelet, and you can see it in the whitish areas. Now, the sphere is a micron silica particle and provides a size comparison for the two. The growth of the calcium hydroxide platelets will cause expansion of the curing concrete if the concrete is not restrained. Growth of the calcium hydroxide platelets will cause the compressive stress to build up in the concrete if the concrete is properly restrained. Shortly after reaching maximum growth, both the Type G and the Type K expansion mechanisms start to relax and dissipate during the drying shrinkage phases of the concrete. The data that we use to plot these curves are obtained from the standard test, the ASTM C878. The test method for restrained expansion of shrinkage compensating concrete for determining the amount of expansion and the rate of the expansion for a given trial concrete mix. And this graph is the one that is used for ACI 223. The bottom curve represents a conventional Portland cement concrete, and note that there's a slight expansion during the initial setting of the concrete. At about the third or the fourth day, conventional concrete then goes into a shrinkage phase. When the curve crosses the horizontal axis, which represents this as a place volume of concrete, the concrete goes into tension and shrinkage cracking forces start to develop. As the tension stresses continue to develop, they reach a point where they exceed the tensile strength of curing concrete and shrinkage cracks develop. Now, the upper curve represents a shrinkage compensating concrete. Now, note that the expansion mechanism is active for about 7 days after the placement. A shrinkage compensating concrete that goes into its shrinkage phase and the concrete volume returns approximately to the same volume at 28 days. Since the shrinkage curve does not go below the horizontal axis, tension forces in the concrete do not develop and shrinkage cracking is thereby prevented. This is the base for developing a mixed design with expansion that meets or exceeds the anticipated concrete shrinkage. And the maximum expansion is typically 1/2 of 1% or less, approximately in line with the ambient temperature expansions. In regards to the concrete growth, we have been using the term expansion as the key description of shrinkage compensating concrete, and it's known as an expansive concrete. These terms are true and accurate, but the following explanation is a key term for these to be accurately reflected. All concrete shrinks as it cures. When concrete shrinks, it goes into tension. Concrete, particularly fresh concrete, is not very strong in tension, and when the shrinkage forces exceed the tension strength of the concrete, shrinkage cracking occurs. Shrinkage compensating concrete expands during the early stage curing, and when shrinkage compensating concrete goes into its shrinkage phase, it shrinks by counteracting the expansion. In order to eliminate shrinkage cracking, we must develop restrained expansion. If we add a shrinkage compensating component to an unrestrained concrete test specimen or a construction member, we will get greater expansion during the initial stage of curing. As the concrete hardens, it will grow and be larger than that at cast volume. More expansion than you would get with conventional concrete. Subsequently, as the concrete goes into its shrinkage phase, there will be more shrinkage cracking. If we provide restraint for the expansion, defined as restrained expansion, the concrete specimen will maintain it as placed volume and no shrinkage cracks will develop. The restraint transforms the concrete expansion into a comprehensive strength in the concrete. And the key to eliminating shrinkage cracking is developing the restrained expansion. The best and the most complete restraint is probably by steel reinforcing, most commonly reinforcing bars, but other means of restraints are available. Restraint is the secret that makes shrinkage compensating concrete work. Restraint is the secret for eliminating shrinkage cracking. Here is how the components make shrinkage compensating concrete work. When the shrinkage compensating component is added to a standard concrete mix and mixing is initiated, two chemical processes begin to happen. and that changes the mixture of the components into the final product, concrete, obviously. The cement begins its hydration process, and the component begins its expansion process. And this is true of both type G or type K. During the initial stage, when the concrete is in its more plastic stage, a small amount of unrestrained expansion that is generated results in a slight expansion or slip of the plastic concrete. And this is true with type G and type K components. As the concrete continues to cure, it is setting and hardening. Also, as the concrete is curing and hardening, it is bonding to the reinforcing steel. As the curing continues, the bonding of the concrete and the reinforcing becomes stronger, and at the same time, the expansion mechanism is also developing and becoming stronger in the concrete. Since the expansion concrete is bonded to the reinforcing, the concrete is trying to stretch that reinforcing. The reinforcing is much stronger than the curing concrete and resists the concrete expansion. The result is that the reinforcing transforms the expansion stresses into a compressive force at the in the concrete. And instead of physically expanding, the concrete is restrained and a compressive force is being built up in the concrete. So shortly after the apex of the expansion curve is reached, the curve goes into a downward slope indicating concrete shrinkage. And the portion of the curve indicates the relaxation of the compressive stresses in the concrete. Ideally, as shown on the curve, the concrete returns to its place volume with a small residual compressive stress remains in the concrete. Here's what we look at when we look at the primary advantages of shrinkage compensating concrete, and especially type G. Shrinkage cracking can be eliminated or greatly reduced when using shrinkage compensating concrete in lieu of conventional Portland cement concrete. This is the reason why we've had this shrinkage compensating concrete was developed. As pointed out in the earlier presentation, contraction joints. It eliminates of the concrete shrinkage means that contraction joints are no longer needed. The cost of installing contraction joints can be saved. With no joints to be sealed, green construction points can be earned by not using chemical joint sealants. The sustainability is also increased since there are no joint maintenance requirements during the lifetime of the structure. And here's the third primary advantage, edge curling. Edge curling can be eliminated in two ways. First, the elimination of contraction joints eliminates the possibility of edge curling as you have non-existing joints. But second, the principal cause of edge curling is differential curling of the concrete with the top surface drying and shrinking first. And at the same time, the expansion mechanism of the shrinkage compensating concrete counters the top surface shrinkage, thereby eliminating edge curling at slab edges and the expansion joints. Now, here's some secondary advantages, and though this isn't all of them, here's four of them primarily. The increased durability of the concrete, the sustainability, greener construction, and economical construction. Now, here we're going to jump back just a little bit and looking at the history of ACI 223, shrinkage compensating concrete, and the publication of various issues of guides and standards for the use of shrinkage compensating concrete. During this era, shrinkage compensating concrete was manufactured using type K shrinkage compensating cement. Type K cements are manufactured in accordance with ASTM C845, the specification for expansive hydraulic cement. Type K cement is an interground product manufactured by the combining of two clinkers before the grinding process, and the mill's standard cement clinker and a type K clinker. The exact proportions of each clinker varies from mill to mill, and minor variations from batch to batch are sometimes experienced at each mill. With such variations, why such variations and differences, might you ask? The answer is that type K is chemically reactive, and normal variations in the raw materials cause changes in the expansion characteristics of type K as manufactured. Similarly, any changes in the concrete mix at the concrete supplier or on the job site can change the expansion rate and the component dosage amount required in the final product. The concrete is placed at the project site. Now, being a type K cement meant that the product had to be transported from the cement mill to the concrete producer for each individual product, and that being a specialty cement meant that the concrete producer would have to have project-specific handling and also storage capabilities. All these factors added the cost to a type K cement project. In the early 1980s, a second product appeared on the market that eliminated or greatly reduced these cost risers and made shrinkage-compensating concrete a more competitive construction material. Now, this new product was a component that could be added in relatively small amounts to any standard mix to produce shrinkage-compensating concrete. In regards to type G components, they are typically added to a standard mix at a dosage rate of 8 to 10% of the weight of the cementitious material in the base of the concrete mix. Now, here's something that's interesting. Let's take another look at the graph that we had previously in 223. You can see the curve, but at this time, let's interpolate the topmost curve as being concrete with the component dosage necessary for a full shrinkage compensating in a typical heavily reinforced structural member. The next lower dosage curve represents full shrinkage compensating of a lightly reinforced member, such as a slab on grade with temperature reinforcing. Conversely, the lowest curve presents concrete with no shrinkage compensating dosage, or conventional concrete. We can interpolate between the full shrinkage compensating curves and the zero shrinkage compensating or conventional concrete curve and develop a set of limited shrinkage curves. Stated differently, by varying the type G component dosage, we can customize a concrete mix to meet any shrinkage parameter specified. Or really, we can say it even another way, that a type G component will provide the same types of benefits that you see in an SRA, or a shrinkage reducing admixture, without the disadvantages that you have of SRAs. Using a type G component in the manner will eliminate the loss of air content and the loss of strength problems that are often associated with shrinkage reducing admixtures. Now, here's some of the dosage rates that we can be able to see. With in the standard in ACI 223 from 8 to 10%, the structural reinforcing, the temperature reinforcing can be able to be seen. And these normal dosage rates, again, from 8 to 10%. Depending on the amount of structural reinforcing that might be required, it could be from 3 to 4% for partial shrinkage control. On projects when there's a shrinkage limitation specified, obviously laboratory tests can be able to be performed to determine that. Now, when we look at the water-cement ratio, the difference here between a type G and a type K can be significant. Type G components are cementitious materials, meaning that they will increase concrete strength slightly due to the small amount of additional cementitious materials added to the concrete mix. The added cementitious material must be included in the water-cement ratio calculations. One major improvement in the type G revolution is that when type G components are used with the water-cement ratio remains as specified. Type G concrete form their expansion mechanism, calcium hydroxide platelets, independently. Type K concrete form their expansion mechanism, or etronite crystals, as we described earlier, by consuming water. Additional water for etronite formulation must therefore be included in the water-cement ratio of a Type K concrete mix. This requirement added additional costs on many Type K projects. Type G concrete does not require any special curing procedures. In essence, a Type G component is transparent in the mix. A Type G concrete placement does not require the special techniques and procedures recommended for Type K concrete. A mister is usually provided to prevent surface drying during finishing and setting, and a 7-day water cure is required for Type K concrete in order to develop that full expansion, as previously talked about in presentations. Both of these requirements add cost to a Type K placement, and both of these additional costs can be avoided by the use of a Type G product. When it comes to the design, the construction and structure, these are the three phases of a typical concrete project: design, construction, and use. There are no changes in the design stage of a project with either Type G or Type K concrete when it's used. Similarly, there is no difference in the finished structure once construction is completed and the structure is put into use. It is during the construction phase, though, that the Type G revolution achieves its greatest advantage. Type G concrete construction in accordance with the standard, and I emphasize in accordance with the standard of ACI 223-10R, recommended construction practices will produce a very high quality product. So here's in the Type K construction, concrete construction requires special techniques and procedures in order to produce a high-quality product. A Type K concrete mix design will vary from project to project, and the Type K mix designs are project-specific. And once a mix design is determined for a project, it must remain constant throughout the project. These special requirements individually and cumulatively add additional costs to a Type K project and are not incurred by a Type G product. Type K construction considerations. The Type G components, on the other hand, are transparent in the concrete mix, meaning that no special construction considerations need to be made. And the contractor's standard placement, finishing, curing techniques, and procedures can be used. And as long as they follow ACI 223, the recommendations for quality workmanship as well. Here's the cost advantages that we can look at from components versus cement. Shrinkage-compensating components are more economical than shrinkage-compensating cements. Transportation, or transporting a bag of component per cubic yard to the concrete producer, is considerably cheaper than transporting cement per cubic yard to the concrete producer. Transportation costs for a Type G component are more economical than transportation for a Type K component, since the dosage rates for the Type K component are typically twice that of a Type G component. During construction of Type K projects, an additional laborer is typically employed to keep misting the concrete to avoid surface drying. The recommended 7-day water cure also requires additional resources added to the construction costs. So what are our conclusions when we talk about the revolution with ACI 223 and the concrete? Oops. Come back to this one. Components are more economical than cements to produce and much more economical to transport to the concrete producer. Type G components are usually more economical than Type K components due to the competitive production costs and the lower dosage rates. Transportation costs vary depending on location of job site and component production facility. Type K shrinkage compensating concrete is more user-friendly than Type K shrinkage compensating concrete and is much easier and more economical to place. Construction costs of Type G component concrete is equal to or less than the cost of conventional concrete construction. So the life cycle cost of shrinkage compensating concrete is always the most sustainable and economical. This is due to the primarily to shrinkage compensating concrete being more durable than conventional concrete, and resulting in less concrete maintenance, the elimination of contraction joint maintenance, the less expansion joint maintenance, and the greater abrasion resistance. By combining these savings resulting from greater sustainability and the benefits of greener construction, a Type G component structure is the gold standard of concrete construction. I'd be glad to answer any questions in Larry's behalf if I know the answers to them. Yes, please.
You mentioned that the reinforcement is really the key to providing the strength. Are there no reinforcement ratios set forth in 223? I'm not familiar with the document.
Yes, there are directions for reinforcement in accordance with ACI 223. In the back?
You mentioned the curing. How long do you have to cure the tank versus the cap?
It doesn't have to be a 7-day cure is not required. 7-day cure is not required. There's benefits to a 7-day cure, but that's not required with Type G.
223 tell us the cure for minimum 7 days?
Yes, and because I think, and I may be going a little outside this, but ACI 223, most of it has been pushed by Type K for years, and so Type G is new, kind of the new kid on the block.
Thank you very much.